Hello, I would like to continue from where we left about probability. So I'll start with talking about interpretations of probability, but actually I made another video about that, a more detailed video, which is actually a bonus video for this topic. So in the content of this video, I'm going to go over this a bit fast. So basically, what is the probability is the question we haven't talked about yet. And in daily life, we use the concept of probability, but that may be a little bit misleading. Actually, it may be a little bit difficult to understand what probability is. This is somewhat similar to the definition of temperature. We use the concept of temperature in our daily lives. However, the scientific usage is a little bit different. Actually, if you recall from your statistical thermodynamics course, temperature is actually the kinetic energy of the molecules. However, in daily life, we never think about that concept. But actually, the scientific usage is confined. The temperature is confined to that kinetic energy. Actually, the resulting energy is temperature is a measure of the resulting energy. So there is a similar or even a much more involved process going on here in terms of probability. So the meaning of probability in science or in statistics is a little bit involved. So there are a couple of competing and sometimes contradictory views about that. So the classical view is, and we use this pretty much often in our daily lives, is the classical view, which is due to Laplace, Bernoulli, and Pascal. This is basically if you have n outcomes in n potential outcomes as a result of a random experiment, the probability of each outcome is going to be equal to 1 over n here. So you have n of these outcomes, 1 over n. The typical examples are throwing a dice, for instance. You have 6 outcomes, so probability is the number assigned to each of these outcomes, which is going to be 1 over 6. And this is pretty much used in gambling. The problem maybe here is actually we assign equal weights to each outcomes, and there may be cases where this is not so. Well, the second one is the axiom of probability, which is due to Kolmogorov. And actually, this is the mathematical explanation of probability, but note that this does say nothing about the empirical content of probability. It's just probability is a number. Actually, it's a function which satisfies these properties. So the sample space of the probability is equal to 1, and probability of any event is going to take a value between 0 and 1. And when I say that probability, you think about the sample space is the all outcomes, and event is any subset. And for two events, E1 and E2, and if they are mutually exclusive, the probability of the union of these two events is going to be equal to the probability of each event. So it's an additive property, or it's an additive function. It's the superposition of two events if they are mutually exclusive. And these rules entails, for instance, other rules that we may obtain using set theory. For instance, probability of complement of event is going to be equal to 1 minus probability of event, and addition rules in a minute that we are going to be talking about. Well, these rules are, without thinking about them, we use these rules in calculating probabilities, but these say nothing about the empirical content of probability. What does probability correspond to in real life? These rules say that there is just a function which satisfies these probabilities, these axioms, and that's all. Now, relative frequency is the one that we are going to be using most of this lecture. It's a very clear concept. It's actually, if it says if you replicate an experiment an infinite number of times, the limiting relative frequency is the probability of an event. So, well, the typical example is if you toss a coin a million or an infinite number of times, which is actually impossible, but a very large number of times, the ratio of heads over heads plus tails is going to be the relative frequency, and probably it's going to converge to 0.5. So you can think about probabilities all in those senses. And as I discuss more about this topic in my other video, in my bonus video, the only problem with relative frequencies is it does say nothing about single events. And this is also an, we can call it an ontic aspect of probability. So it is an objective probability that the probability is carried with the system. It's not due to the observer, we may say. This might be a little philosophical, but anyway, as opposed to this, looking at from the observer's point of view and giving a subjective character, we have the subjective, or usually the most frequently used subjective probability, Bayesian probability that we have. So it is the degree of belief here. So as opposed to an ontic quality here or ontic property here, now we have an epistemic property or quality that we give to the probability. So probability is not in the system, but is in the eye of the observer. So therefore, we have the degree of belief. So chance of rain tomorrow or today is 30%. For that statement is actually our belief that there's going to be rain today or tomorrow, whatever. Compare it with relative frequency. Here, relative frequency actually means that of all the possible tomorrows or today's, an infinite number of today's, 30% of or 10% or whatever percent of these all possible outcomes, there's going to be rain. But note that there's going to be only single today or single tomorrow. Therefore, relative frequency seems to be a little bit difficult. It seems to have a little bit difficulty of explaining the probability here. So the subjective probability may be a better choice. Anyway, but most of our course will be about this relative frequency interpretation. But nowadays, especially in machine learning communities, subjective probability, Bayesian probability is also very much commonly used. All right. So actually, addition rule. This is not an additional rule. Although it's an additional rule, it's not an additional rule. I may say this may be derived using Kolmogorov's axioms. Actually, if A and B, well, think just here, the third axiom says that if E1 and if E2 are mutually exclusive, if they do not, if they have an empty set of intersection, then you just add their probabilities to find the union of the probability of the union of these two events. But if they intersect, actually this can be derived using the simple set operations. Probability of A union B is going to be equal to these two probabilities, and we are going to subtract the intersection of probability of A and probability of intersection of A and B. Well, for three events, the equation gets a little bit complicated, but these can be easily derived using Venn diagrams if you like. Oh, by the way, for most of the course, we are going to be dealing at most two events. More than two events, we are not going to go into. All right, now comes a couple of definitions, but these definitions are going to be also pretty much intuitive, so that we are going to enrich probability. One of them is conditional probability. Now, conditional probability is a probability of an event given some information about some other event, and it is shown in this manner. Probability A, this is actually a vertical line like this. This is not the complement sign that I have used previously. Please note that. So this means given A, probability of, given B, probability of A. And it is defined in this manner. This is actually this is the only a definition in words. In mathematical terms, it is probability of A intersection B divided by probability of B. Now this may seem complicated, but actually it's not. It's very intuitive and it's very straightforward. The idea is this: we just concentrate on the probability of B, only the set of B, and probability of A intersection B, this A intersection B should surely be a subset of B, because B is the larger set here, and there's going to be A here also, and there is that intersection of AB. Therefore, compare it to B. This is going to be just a subset of B. So this probability, since this set is smaller than this one, this probability on the numerator cannot exceed the probability on the denominator. Hence, this probability, this resulting measures is going to be still a probability. It cannot exceed unity, and it's going to be, of course, greater equal 0. So in this case, and the meaning of this is also pretty much straightforward. Now, once you find intersection of B and A, it's this region here. We are trying to find the probability with respect to the total probability of this B here. So it's a kind of normalization of this region with respect to B. So this is going to be also a pretty much intuitive definition of conditional probability. And well, one example, maybe a typical example. Let's say that tomorrow it's going to, all right, let's say that this is the temperature. All right, let me put it that way. That wasn't not a very good example. A better example, whether temperature is going to be 25 or, all right, let's say that there is such a probability. And of course, it's going to be the opposite probability of T smaller equals 0 Celsius for tomorrow. We are given this probability. And there is also whether tomorrow is going to snow and no snow. Of course, this is going, if you call this P, this is going to be 1 minus P. If this is going to be Q, this is going to be 1 minus Q. So these are single event probabilities. Now you may ask this question: what is the probability of snow tomorrow, given that we have this event or this one? Note that it is pretty much, although I haven't given any more details about the question, if temperature is smaller than 0 Celsius, it is pretty much likely that the probability of snow will be larger than this value. Why? Because actually, well, you may look from two different perspectives. From this, it's actually easier to understand from the subjective perspective, I think. How much information that we have on the system, it's easier to understand from this perspective. If no information is given about the temperature, we only have this probability. Let's say 30% of snow there's going to be tomorrow. We have only that information. However, if we know that temperature is going to be low, then the probability of snow is going to increase. Or maybe it's going to be independent, as I'm going to say in a couple of minutes. But this is what the conditional probability means. And additional information on another variable may affect the probability of this variable. So whether it's going to be tomorrow, it's going to be hot or warm or cold, will have effect on the probability of that other event. Well, a very simple example. Well, this is actually too much simple. Let's say that we have that many of air samples collected, and for each 266 of these samples, we check whether a certain molecule A is present and a certain molecule B is present or not. And we give equal weight to each of these samples. So here, actually, we use the classical interpretation of probability. Each sample has the same probability of being chosen. Anyway, So if these are the event definitions, A is the event that molecule A is present in a random sample. So we have these 266 samples, and we have these molecules here, for instance, in 212 of these 266 air samples, we have no A molecule and we have no B molecule. And the question is, if you put them in a container, well, it's a bit of a silly question, but if you just randomly select one of those samples, then what's going to be the probability of A? The event that molecule A is present, probability of A. Well, this is pretty much simple. So this is going to be probability of A is going to be equal to, let's see, we have probability of A here, 24 plus 12 over 266. But here even, let me just write the result. Let me do this operation slightly more formal way. Probability of A is going to be equal to, note that this is probability of A intersection B plus probability of A intersection complement of B. Why is this? Actually, just refer to the third axiom of Kolmogorov. He says if two events, call this E1 and if E2, if they are mutually exclusive, then you can add their probabilities. Now, are these mutually exclusive? Yes, they are, because here A is, think about this, A and B. Here it says A intersection B, this part, great. A intersection with the complement of B. Now the complement of B is this area, which is going to be very difficult to show here. All the shaded region, all right? I'm sorry, no region here. It doesn't include B here. All right, now it looks better. So actually it's going to be B complement is all this shaded region except every part of this B, and where it intersects with A is this part. So this is the first shaded region, and this is going to be this region. And if you sum them, note that they have nothing in common. It's going to be probability of A. So probability of A intersection B means that both A and B is in that sample. So it's going to be this case. Both there is A and B. So it's going to be a probability of 12 over 266 plus probability of A but not B. Probability of A, right? A is there, but no B is there. So it's going to be 24. So the very same number is obtained. So note that the formal way of solving this question is by this method. It helps you. Well, at the beginning, please try to solve the questions of related with probability using these approaches, right? After a while, once you get practical with that, once you understand the basics, you can be more practical. But for the time being, just do these calculations. Anyway, so here we have answered already two questions. Probability of A intersection B is 12.12 over 266. So we have two answers here and here. That's great. What about the conditional probability of A given B? Now, there is usually a confusion about these two concepts. The difference between intersection of A and B and A given or A given B. Now the difference is this: probability of A intersection B is, here the probability is with respect to the total sample space. So it's going to be only this area with respect to the sample space. On the other hand, here, as I tried to say previously, here we kind of normalize the probability of A with respect to B. So that's the important point here. So here, probability of A given B is going to be, just using the definition here, it's going to be, if I can find my pen, yes. divided by probability of B. It's just the definition I have used. And note that it means the intersection of A and B, which one may easily be confused about these, whether these two terms are different or not. They are different. It is actually the intersection normalized with respect to probability of B. So probability of A and B is going to be 12 over 266, and probability of B is going to be equal to, where is our probability of B, is going to be using the very same logic for probability of B here. So probability of B is going to be equal to intersection and the intersection with the complement of A, but I'm going to do it a little bit fast. It's going to be, where is our B? Yes, here, yes, here. So it's going to be 18 plus 12 over 266 is going to be 30 plus 266. Therefore, I put this value here, 30 over 266, and the result is 12 over 30. And this is the final result. Now, let's also see whether our intuition says the same thing, right? And we can obtain the same result. Now, without using this equation, and I want you to use this equation, but I also want you to understand intuitively, heuristically what's going on. Now, given B, which means there is B in our system, it means we are in this row. What is the probability of having obtained an A? Now, given B only contains or comprises these samples. So there are 30 samples here which are involved. So the new sample space is going to be those 30 samples. And among these 30 samples, the events are that we are interested in is only revealed in 12 of these samples. Therefore, this is going to be probability of A given B. Using our intuition and using our equations, we obtain the same result. But I repeat again, I want you to apply this method. All right, now we have a couple of more rules, but these are just the same, the variations, nothing new here. Let's see. Now, since we have already learned the conditional probability, now we can use in vice versa. In some questions, conditional probabilities are directly given, and we would be interested in intersection of two events. So in this case, of course, you can write the equation in this manner, and on the right-hand side, if these values are given, you can easily compute this equation, this quantity here. And there is another approach which we are going to be using in Bayes' theorem in a couple of minutes. So you can write this equation in two different sizes. Note that this can be also written as this way. So two different conditional probabilities equal to each other. So if three of them are given, you can easily find the other one. Now, this is a very useful rule, and this is still nothing new here. And I have already talked about this. B as a set is going to be equal to A intersection B union with A complement intersection B. And this is going to be equal to B. When did I talk about that? I talked about that here. All right, here. Well, there is actually a nice caricature of, not maybe, but a caricature, but a schematic representation of the system here. Since these two sets are mutually exclusive, now we can easily use the Kolmogorov's third axiom. But here, further thing can be done. Since we have already defined conditional probability here, instead of these terms, we can write the equivalent representations for conditional probability. So for conditional probability of A intersection B, we can write this equation. And for this part, we can write this equation, and we can find the total probability of B. Well, the equations are straightforward here. What may be confusing, and as I'm going to show in the next example, is the meanings of these terms for each of these terms. When the question is given in a story form, you should convert the story form values or given information into these mathematical formulations, and one may really need to understand the meaning of these conditional and the total probabilities, each of these, so to be able to equate or associate the given information with the mathematical formulation. Okay, let me try to solve an example and see how these can be used. So we have, let's say, a factory, and this factory manufactures chips, and as raw material comes, and let's make it very simple. During the manufacturing, there are two possibilities. There may be contamination, or everything works fine and there is no contamination added or mistakenly added during the manufacturing. And once chips are produced under these conditions or possibilities, these chips may work fine or they may fail. Note that this is the important part. It doesn't necessarily mean that if there is contamination, chips will necessarily fail. There may be contamination, let's say some workspace or some other conditions, whatever, but still the manufactured chip may work fine. And it is also possible that everything seems to be fine, there is no contamination, but due to some other effects or I don't know, some things that we haven't considered, that chip may still fail. But this is the only variable that we have paid our attention to. So there are two random variables here. Whether a chip is contaminated or the manufacturing is contaminated or not, and whether chip is going to work fine or is going to fail. So there is some information given in the question, and usually these information will be given in a wording form, in statements in words. So you have to change everything to mathematical representation. So this says that product failure if chip is contaminated, a certain probability is given. Product is going to fail if chip is not contaminated, some probability is given. And probability chips being contaminated, some probability is given. Now the question is, what is the probability that a randomly chosen chip fails? Now, in order to solve these kinds of, actually any kind of probability question, we should, I think for me at least, the easiest way is to convert everything to mathematical terms so that we can continue with the mathematical formulation. So in order to do that, I use some event definitions. I use F for product fails. You can use, of course, anything that you like. And the second one is going to be product, let's name not product, but contamination during manufacturing. Okay, these two events are defined, and note that in order to solve the question in an easier or more difficult manner, even the correct or the convenient choice of events is also important. All right, now let's try to convert what is given in the question in wording to these symbols. Let's see. Now, chips being contaminated. Any chip being contaminated, contamination during manufacture, this probability is given. And once we do that, we can more easily see what's going on. When these numbers and this in story form, this whole thing is given, it's difficult to understand. Now we have an understanding of, with 80%, there's going to be no contamination in the manufacturing. That's great. Let's continue. Now these two, and we have used this information. What about these two? Product failure if chip is contaminated. One thing I tend to realize among students in previous years is they tend to equate this to failure if chip is contaminated, something like this, and they write this as 0.10. Now let's see if this is indeed given. This means that the product will be both failure and it means it should have been also contaminated. Note that this is not what is suggested by this statement. If chip is contaminated, given that you know that chip is contaminated, product failure is given. Hence, this is not actually what is given here. What is given here is product failure given that chip is contaminated. So think about that. You know that chip is contaminated, product failure is 0.10. Now this is also being used. So this also gives an idea about only 10% of the contaminated chip fails. That's great. That's great. Let's continue. Product failure if chip is not contaminated. Now this is very similar. This time not contaminated, I use the complement. This is 0.05. And there is also 5 out of 1,000 these chips will fail. Oh, by the way, what do these probabilities mean? We can easily equate them, or we can use very easily interpret them as historical information. There are so many batches, so many runs in that factory. It's of course not infinity, but with a very large number, these relative frequencies have been obtained. Therefore, we believe that these relative frequencies are still maintained for future operations. Hence, we do the calculation. So now these are the given information. Now still there is something missing. I haven't changed I haven't mapped the question asked to mathematical terms. It says a randomly chosen chip fails. This means here all these chips are collected here, and you randomly choose without knowing whether they are contaminated or not contaminated previously during manufacturing. You just randomly choose one and you see whether it's going to fail or not. So the question is actually this one. So what is asked here is referring to the previous thing that we have covered. We are asked a total probability, whereas many information or some information about these conditional probabilities are given. So now let's continue. Now, can I write the total probability in terms of these conditional probabilities? Yes, I can. I can also easily write this way. This is just an application of the third axiom of Kolmogorov. Note that it is the intersection of these two, is F and C complement, and note that they are going to be mutually exclusive. And instead of this term, I'm going to write probability of FC, probability of C, and instead of this one, I'm going to write F. And once you actually bring it into this form, as you can see, it's pretty easy to handle. This value is given, it's going to be 0.10 times probability of C is 0.20. Probability of F given C complement is 0.005. And probability of C complement is, note that C complement here is a complement, is the total probability is 1, is going to be 1 minus 0.20. And the result is going to be equal to 0.024. And note that this value is, using your intuition or heuristics, this value is between those two values. What do I mean by that? Without having any information whether the manufactured chip has been contaminated or not, we have a 2.4% of picking up a chip which fails. If you have some knowledge about the contamination, if you know that it's contaminated, this is 10%, a higher value. If it's not contaminated, if it is 0.5%, a low value. And if you have no knowledge about whether it's contaminated or not, it's a value between those two, which makes sense. So please also make sure that you get the idea. Okay, so the next topic that I would like to talk about is the concept of independence. Now, similar to conditional probability, this is both a definition, but this also makes perfect sense heuristically. So the idea is, first, the heuristics, two events are independent if and only if any of these three statements is true. But as I said, the first heuristics, the idea here is in independence, the realization of one event does not change the probability of the realization of the other event. This is the concept of independence. So actually, any of these three conditions mean the same thing. This is the most generally used one in numerical computations, where it says that probability of A intersection B, this new event, is going to be equal to probability A multiplied by probability B. I guess some of you have seen this even in high school. But I think these two makes more sense compared to, or it's easier to understand. This says that, let's try to read this first statement, for instance. It says that probability of A given the occurrence of B is equal to probability of A, which means that whether event B has occurred or not, it does not change the probability of A. And this is exactly the definition of independence, two events being independent. Well, this actually, the definition or the explanation is more like an ontological explanation. Now, from an epistemic point of view, this means that the event, whether we know whether event B has occurred or not, does not change our information about event A. This is what the idea is. For instance, we can say that there is an event, call this A, for instance, this event. Let this be event equal to, let's call it E1, having a letter grade of A in a course, in a specific course. And event 2 is going to be equal to, let's say, failing in the same course. In the same course. So now the idea is this, or the question that we should ask is this: whether this is equal to E1. Actually, we should realize that if we know that we fail in this course, the probability of having A in this course is going to be equal to 0. On the other hand, without knowing that we fail in this course, or we are talking about a student, there is going to be always a finite probability of having an A grade in that course. Therefore, these two are not independent from each other. I'll come to that example in a minute again, but that's one example. Now, there is a proof which states the relation between C and A and B. If you cannot see it, very straightforward. It simply says that probability A given B is equal to this definition that we have seen. A and B, if they are independent, we can replace this numerator by probability A times probability B, because statement C states that. In this case, probability B will cancel, and we are going to have probability A given B is going to be equal to probability A, which is one of the, which is actually the first statement stated here. Therefore, if statement C holds, then statement A will hold also. But it's also vice versa. If statement A or B holds, C will also hold. Now, an interesting point, and that's where this example will come into play again. If A and B are mutually exclusive, what does this correspond to being mutually exclusive in terms of independence? One may tend to think at first sight being mutually exclusive also mean being independent, but it's actually quite the contrary. Now let's analyze it mathematically. If A and B are mutually exclusive, then this is the mathematical representation of being mutually exclusive. And hence, probability of A and B happening together is equal to 0, because the intersection is an empty set, and the probability of an empty set is going to be equal to 0. Now let's write the conditional probability rule. It's this one, probability A given B, because we would like to, why do I write this? Because we would like to obtain a relation something like this, so that we can say, or we can determine whether they are independent or not. All right, now probability of A and B is going to be equal to 0. Hence, probability A given B is equal to 0. Now let's go back. If this condition were to hold, then we would have said that A and B are independent. On the other hand, when A and B are mutually exclusive, this is the condition that we obtain. So can we reconcile these two? Yes, but only if probability of A is equal to 0. So here is the idea. If probability of A is not equal to 0, right? And if A and B are mutually exclusive, so if these two conditions hold, then A and B are not independent. So that may seem interesting, but if A and B are mutually exclusive, then most of the times I'm talking about this condition, then A and B are not independent. And it makes perfect sense. Let's go back to this example. Note that for this case, E1 and E2 are mutually exclusive, because a student cannot fail and cannot get A at the same time. So if they are mutually exclusive, then as we have talked for this case, probability of E1 given E2 is going to be equal to 0. This is not going to be equal to probability of E1. Hence, they are not going to be independent. Right? Usually we say not independent instead of dependent, but that's okay if you prefer that one. All right, so one last point, and this part is actually summarizes the points I have talked about. For multiple, let me erase this part. For multiple events, how can we determine independence? As I said previously, I think in this lecture or in the previous lecture, we are not going to talk about multiple events, but up to only 2 for the sake of the introductory spirit of this course. But you should have some idea, even at this level, for multiple events, all subsets of these events should hold this property. So if you have 4 events, let's say, then all subsets of 2, E1, E2, E2, E3, E3, E4, all of them should hold this property. And also for any 3 events out of 2, and also 4 events altogether, their intersection should be, the probability of their intersection should be written as a product of independent or each event's probability. If you can do that for all subsets, then these 4 events or all these events are independent. Now comes the last topic, Bayes theorem, which is itself a very interesting topic. Itself is actually graduate level course. And as I stated previously, this Bayes theorem is usually related with subjective probability, degree of belief, the epistemic probability, which states that as opposed to the frequency interpretation, if you watch the interpretations of this probability video, you're going to understand the whole picture more completely. The Bayes theorem belongs to the interpretation of probability, which states that probability is in the eye of the beholder. It shows us how much information we have upon the system, upon any system, as opposed to frequentist interpretation, which states that the probability is a property of a system itself, which reveals itself in the long run of experiments as a relative frequency. Okay, anyway, but we're just going to touch the Bayes theorem topic here and not going into this subjectivist interpretation. But just for the curious souls, if you are interested in, for instance, machine learning, you have to learn Bayes theorem and Bayes applications. Anyway, so the idea is very simple and nothing new under the sun in terms of equations, but in terms of interpretations, yes. The equation that we use is simply this one. Again, the conditional probability rule. Now, as I've stated previously also, we can also write this numerator in the opposite order. What do I mean by that? Here, this side was probability A given B times probability B. This part will be probability B given A times probability of A. Then you see there are 2, actually, this part here, this side and this side contains 2 conditional probabilities, but they are conditioned on each other. So if you get rid of this middle part and if you write only this part, we have this representation, actually, probability A given B is equal to this whole thing. So what's the big deal? Actually, if I write it again, but if I take P a little bit out separately, so I write it P A given B is equal to some term times PA. Now, what does this represent? This represents something very interesting. Now, probability A is what we call total probability, which means, again, well, here when it comes to Bayes' theorem and this representation and this interpretation, it's easier to think of a degree of belief kind of interpretation, as I said. So I'm going to use this one. So we have a prior belief about an event A. For instance, we are talking about, let's say, Barcelona is going against a certain team, and it's not a very strong team, let's say, right? And so, what's the probability of Barcelona winning the game? Is this probability of A, let's say, and this one will be probability of A given some additional information about B. So there is an additional event B that has occurred. So given this additional B occurrence, what's going to be the probability of A? So let's say that this B is that additional information, and let's make it an important one. And we now know that, well, this information, nothing else is known about using the whole information about the Barcelona history or things like that, you come up with some probability. Now the additional information is this: Messi is injured and he's not going to play the game. So that B is that event. Now, given this information, probability of A will change. So this interpretation of Bayes' theorem is simply some prior probability is going to be converted to a posterior probability upon giving some new information about some event called B here. So that's, and this, I'm not going to talk about the details about this function here. This is called likelihood function. Again, this is just these terms, but I just interpret it from a subjective probabilistic point of view. And as I said, I'm not going to go into detail. That's, I think, sufficient. So actually, that has very interesting applications and implications. And actually, this example will, I guess, is going to give a glimpse of those interesting applications. Let's read the example, then talk about it. A rare disease is seen in 1 million people. All right, so at the very beginning, a probability statement is given with no further information. Through randomly choosing people in a population, 1 in 1 million is sick of that disease. Now, we have a blood test to apply on the people, so for the diagnosis of this disease. And this, as you can see, is pretty much similar to that COVID-19 thing. So the test correctly detects the disease with 99% if the person actually has the disease. Sensitivity is 99%. Now we are in new waters, I may say. Probably this is something that you have not encountered previously in any other course, and even if you haven't thought about it in detail, this might come as something novel. Now, when we are talking about these medical tests, these diagnostic tests, they have always two sides. We cannot simply say that this test is effective, for instance, for 90 times or 90%. We should elaborate, or we should distinguish between two concepts. And these concepts is, let's say that there is a person with a disease, and I'm going to show the disease with, let's say, a bar here. So this person has a disease. And if that person is tested, and let's show the test with this, maybe a test tube could have been better. All right, let's make it like this. So this is our test. This test will result as a positive or a negative. Now, positive means this test results find that person, finds the disease in that person. So positive has nothing to do with the positive, nice things, blah, blah, kind of thing. So that person actually has the disease, but of course we do not know it. We just apply the test, and the test says that yes, that person has the disease. And this first statement says that if a person with the disease comes, with 99% probability, that person is diagnosed as having that disease, and 0.01% he or she hasn't got the disease. This is a test result, and this is called sensitivity. Sensitivity, yes, I think I spelled it correctly, 0.99 or 99%. However, that's only half of the picture. It's not the total picture. Now, the second statement tells something else. The test erroneously detects false alarm, the disease, in 10% of people who are actually healthy. Specificity 90%. Okay, so in symbolic form, this is the story. And this is not specific to this question. In all diagnostic tests, or many tests also in engineering or in other sciences, this is the case. Maybe in those other cases, humans not with the disease will not be the subject. There will be other things, but nevertheless, you are going to have an item that may be a human, an organism, or something inorganic, whatever. You are going to pass it through a test. The test is going to search for the absence or presence of something, and it's going to give the answer. Now, this person doesn't have the disease. And again, he or she has applied the test. Now, this test gives a positive result. Now, here, positive means that person has the disease. This is what the test says. Note that actually this should be 0% under ideal conditions, because there is nothing wrong with the guy. However, the second statement actually says that for actually healthy, 10% an error is committed. Note that this error here is 1% or 0.01, and this is 0.10, let's say. This one is a different error from this one. And here we have a negative result for 90% of the times. And this is the correct result, 90%, and this is another correct result. Note that there are two different correct results, or two different values for correct results and two different values for erroneous results. Therefore, we have actually two different matrices for all measurements. And these are usually called, I'm not going to go into those details because it's a little bit out of the scope of this course. Nevertheless, this is pretty much parallel to what we are witnessing right now about the COVID-19 cases going on, with the test being positive or being reliable or not, kind of thing. So we have the concept of true positive rate and false negative rate. So if you would like to have more information about these concepts, which you are not going to be responsible for the course, but for the sake of your feeding your satisfying your curiosity, because the previous year students were pretty much interested when COVID-19 incident have occurred. We were in the second term around March. Most of them said that they remembered these from the statistics course, and due to that I prepared a video and I posted it, and actually I'm going to give you the link under this video, so for the curious souls you can check them. Anyway, so this is the general picture here. So for any test, a single a 90% success value, for instance, is not sufficient. You should ask the question whether that 90% success or 99, whatever, is confined to people who have the disease or who don't have the disease. So we should have two different values here to evaluate, to assess the quality or the reliability of a test, diagnostic test. Anyway, now let me get rid of all of these, because these are, as I said, general information about what's going on. Actually, if you watch that video, you're going to realize that a 100% for both cases, for both specificity and sensitivity, is impossible. Therefore, you should sacrifice, unfortunately, for some of them. All right, now the question: if there is a person who goes to have the test, and if the test result is positive, the test has given an alarm. It doesn't mean that I repeat. It doesn't mean that everything is okay. It's just the test says that there seems to be disease here. Then what is the actual probability that the patient actually has the disease? Now that's I think a very interesting question. That seems like a dramatic question also. This is a rare disease, but the test comes out to be positive. Then should the person be frightened or be afraid that he or she has the disease? Quite possibly you seem to think yes here. And let's see what the Bayes theorem will tell us. And what does that got to do with Bayes? First, conceptual, let's think about it. Without any further information, that is the test information, what we know is we have only 1/1 million chance of having that disease. This is a prior probability. When we have a positive test result, how is that the prior probability change into a posterior probability? That's what is asked. All right, so what I'm going to do is, as I stated previously, first I'm going to define a couple of events, and I think defining the events, as I said previously, is the most important part. Actually, for this question, I think it's much more important. So the way I define the events is by this way. I define that this is the event that patient has disease. This is how I define D. And I'm going to define another event, and this part is a little bit tricky. If I were you, I would work on my own before seeing this, because using different definitions, you can come up with different ways of solving the question. This is the event that test result is positive. So this is the actually that patient has that disease. This is the test thinks that that person has the disease. Here it says positive. All right, so let's now write everything in terms of these events, what are given. Now, probability of disease. With no further information, as I said, it's easier to think in terms of, from an epistemic point of view. Let's think about now in terms of information here, right? No information is given here, so the only information about is a guy among the whole population. So probability of that disease, having that person have disease, is 1 in a million. Now the other ones. This statement, test detects the disease with 99% if the probability is actually has the disease. Given that person has the disease, the probability of test giving a positive is 0.99. And note that this is exactly sensitivity. And now the other one, the last one, is going to be probability of this time that person does not have the disease. Given that that person does not have the disease, yet the test erroneously gives a positive test result, is 0.10. And what does the question ask? Good question asks, given that the test result is positive, what is the probability that that person has the disease? This is what is the question asking. So we have these terms given, and this is what we are asked. And what we are going to do is directly apply this concept. But if you were to see this question for the first time, or let's say a couple of chapters later, wouldn't you be confused? Yes, then you should realize that what are given are conditional probabilities and another conditional probability is asked. So this is probably very much a Bayesian problem. And now I'm going to write this, liken it to this equation, or this equation. This one is going to be equal to probability of, let's say, TD D over probability of T. Actually, I have exactly likened it to this equation. Please check that this is correct. So actually this is, where did I come up with this one? This is Bayes' theorem. And actually, where does this equation come from? This is just due to the axioms of, Kolmogorov, and the definition related with conditional probability. Now, do we have all the information here? Let's see, we have this one. We have this one. What we do not know is this total probability of this test giving a positive result. For this one, we are going to use the total probability rule. It's very simple. This is going to be, since there is one event here, this is going to be again application of Kolmogorov's third axiom. We can write two probabilities exclusive, which have no, which are mutually exclusive. Then I'm going to convert them to conditional probabilities. This one and the second one. This one is going to be probability D. Now let's see what we have here. This one is given. Where is it? Probability of D. Yes. I'm sorry. 10 to the power minus 6. And probability TD 0.99. And I highly recommend you to leave this part and to do the calculation here explicitly, because I'm gonna come to that, and I'm gonna give you a couple of hints about that. And then let's see probability of TD 0.10 and probability of D complement is going to be 1 minus 10 to the power minus 6. So if you do the calculation, this is going to be approximately equal to, let me see, I'm going to copy it somewhere here. It's going to be approximately equal to 0.10. So when we write these values here, the probability of dt is going to be equal to t given t is 0.99, 0.10 multiplied by 10 to the power minus 6, and the result is going to be approximately equal to 10 to the power minus 5. So now when you find the result, let's see whether it makes sense. It says that before any test, you had this probability, or that person has that probability. The test has turned out to be positive, yet the probability of that person having that disease is 10 to the power minus 5. Now, what does that mean? That means, first of all, well, that's the first of all interesting result. Why that has come out to be, please go over the calculations and make sure that there is nothing wrong here. So why does this is a little bit counterintuitive. Try to absorb this idea. But once you absorb this idea, you should realize that this test is practically meaningless or useless. If you come up with that test and say that, okay, this is going to be useful, actually people will do this calculation very quickly and say that this is useless. Why is this useless? Because that is such a rare disease that this much of specificity and sensitivity, please go over these calculations and see how to make this value much, much larger when the test result comes out to be positive. Try to come up with or try to find a method to do this. So which of these sensitivity or specificity should be increased, and how much should it be increased so that this test will be really useful? And even with those seemingly large values with 99% of sensitivity and 90% of specificity, as I said, this is pretty much useless test. Okay, and as I said, please go over this calculation. Just try to especially concentrate in this region, which of these values should be increased, right? So that please note that you cannot change this value. It is what the disease, the probability of disease in the community, you cannot do anything about that. What as an inventor, as an engineer, you can do is just try to come up with new tests or equipment so that you are going to change these values. And how should your test, which of these values should be increased so that you get a reliable set? Okay, that's all I'm going to talk about. See you next time with, I think, discrete probability distributions, and see you.